Hey, what's up? It's Mr. Cook, and we are going to do the section 2.7 in class practice. Okay, so this gets us ready for the test that's coming up. This is the big problem that we worked on. So this is just an example of how the test is going to look for that question. You know, just like what it does in the test review and every other test review, we show you exactly how the problem is going to look. So there's no real surprises there. Okay, so. One thing that's nice to have is a graphing calculator. So if you have a graphing calculator, you want to get that out right now. If you don't, that's okay. We'll try and do as much of this as we can without a graphing calculator. Okay, so start off with the total number of zeros. That's what part A asks. What that really means is that it's just looking for the degree. So the degree is the biggest exponent on this entire expression. That's 3. So that means that the total number of zeros is 3. So that's pretty easy. And then once we have the degree, we can also answer the number of terns that we have here, because it's just that number, 3 minus 1. So what's 3 minus 1 equal to? 2. So there's going to be 2 terns. That's about as easy as it gets. Another thing that we can answer real quick is the end behavior when we have the degree and the lead coefficient. So this x to the third is a positive value. So since it's positive and it has an odd degree, that means that the end behavior starts pointing downwards on the left and ends by pointing upwards on the right. Okay, so that's end behavior. And then let's see here. So finding the total number of positive real zeros, we just count the number of times that the signs change on our original function. So it starts off positive and stays positive and stays positive and stays positive. So that means that since the sign doesn't change at all, there's no change whatsoever, that means that there are 0 positive real zeros that we have here. So that means that all the positive real zeros that we have from these 3 should be negative. Let's see if that's the case. So we change the sign on all of the odd degree powers. So we change the sign on this x to the third, it becomes a negative x to the third. And then it has an odd exponent on x, so that turns into a negative 15x. But everything else stays the same. And we do the same thing. We just check to see how many times the signs change. So it goes from negative to positive, so that's 1. Positive to negative, that's 2. And then negative to positive, so 3. So we could have 3 negative zeros. Or if we have the presence of an imaginary number, we could have 1. So on your test, I would just want you to put the maximum number 3, and that'd be acceptable for me. Okay, so that's all of part A. Part A is all done. Now we're going to do part B, which is to determine the number of possible positive and negative rational zeros. So this is just using the rational zero test. And what we do for this is we take the lead coefficient, and so that's like the number that's out front of the whole thing. So in this case, it's just the number 1. So we just take 1, and then 7 is the constant value. And we put 7 in the top, 1 in the bottom. We list off their factors. So the factors of 7 are 7 and 1. List off the factors of 1, which is just 1. And then we make fractions out of this and turn them positive and negative. So these give us all the possible rational values that we could possibly use for this. So let's see how this works out. You have a denominator of 1, so 7 over 1 is 7. So we could either have positive 7 or negative 7 as a possible zero. And then also 1 over 1, which is 1, so positive 1 or negative 1 as a 0. Now it says to, for part D, find all the zeros. So we use all of these possible rational zeros, and we plug them in to synthetic division to see if any of them work out. So we're just going to use the synthetic division algorithm on one of the 4 numbers that we have here, so positive 1, negative 1, positive 7, negative 7. And see if it works. So let's go ahead and set it up. So we have a corner, and then 1x to the third, 9x squared, 15x, and then 7. So then just pick a number to put there. I'll put, I guess I'll just start with positive 1 and see if that works. So if it works, then that means that we will have a remainder of 0. So at the very end, that remainder box that goes under the constant, that should be 0. So let's see if that's the case. 1 times 1 is 1. 9 plus 1 is 10. 10 times 1 is 10. And 10 plus 15 is 25. 25 times 1 is 25. And 25 plus 7 does not equal 0, so this is not a factor, so we can just eliminate 1 from our possible zeros. Now let's try another one. So if 1 doesn't work, let's try negative 1. So negative 1 is what we're going to plug in. And the same numbers, 1, 9, 15, 7. And we check that out again. So we want 0 for our remainder. Let's see if we get that here. 1 times -1 is -1. 9 minus 1 is 8. 8 times -1 is -8. 15 minus 8 is 7. 7 times -1 is -7. And 7 minus 7 gives us 0. So this is one of our zeros, a -1. Okay, so now let's work with this stuff over here, 1, 8, and 7, and let's try -1 again, because whenever you get 1 0 that works, try it again. It might work again for a multiplicity of 2. So let's try it out again, -1. See if that one works out. All right, again, we're looking for a remainder of 0. Let's see if we get it. 1 times -1 is -1. 8 minus 1 is 7. 7 times -1 is -7. And, sure enough, it works again. So this gives us another one of our zeros, a -1. And remember how many zeros we're supposed to have? We're supposed to have a total of 3. We already found 2 of them. And our last one can be found with this little tiny linear equation right here. Because what this turns into is 7 is our constant, 1 is our x, so x plus 7. So that's a factor of the polynomial, and if we set that equal to 0, we can solve for our last 0. Just subtract 7 from both sides and you get x equals -7. That's your last 0. So the last number that would have worked would be -7, and I can show you that -7 works on our polynomial real quick. -7 in the corner, and then we have 1x to the third, 9x squared, 15x, and 7. So check it out. 1 times -7 is -7. 9 minus 7 is 2. 2 times -7 is -14. 15 minus 14 is 1. 1 times -7 is -7, and we get another remainder of 0. See, so I can even prove that -7 is one of my zeros from there. Okay, so now we're going to find the y-intercept. So the y-intercept, we get that by just plugging in 0 for x and finding the corresponding y value. So we're going to plug 0 in for x for our equation. So we get 0 to the third power plus 9 times 0 squared plus 15 times 0 plus 7. So that's going to be 0 plus 0 plus 0 plus 7, which is just 7. So 0, 7 is our y-intercept. Going back over to the zeros over here, if we have -1 and it shows up twice, that means it has a multiplicity of 2. So what we would write out is -1 with a multiplicity of 2. And this means that this x-intercept that we have, -1, 0, since it has a multiplicity of 2, is going to touch off of the axis, the x-axis when we graph it out. For this one, -7, it just has a multiplicity of 1 because it only shows up one time as a factor. And since that's the case, our x-intercept, -7, 0, is just simply going to cross directly through the x-axis. Okay, so we've already got a ton of stuff that we can graph out. The last thing that we need to do is just write the function in factored form. This is really, really easy. We just use the steps that we learned in the last couple sections in the review, and just write up the factors with their multiplicities. So if the factor is -1, then if the 0 is -1, then the factor is going to be x plus 1, and if it has a multiplicity of 2, then that means that it's squared. If we have a 0 at -7, then that means that we get the factor x plus 7, and it has a multiplicity of 1. So we can just we could write a 1 up there if you want, just to remember that it's a multiplicity of 1, but you don't have to. You can just leave it as x plus 7. Okay, so now that we have all of this information, this is a ton of opportunity to get partial credit if you know how to do some of this stuff. Now the rest of it is just to graph it out. So you can obviously use your graphing calculator for a good chunk of this, but I'm just going to graph it out by hand because I have all the stuff that I need to graph it. Like my y-intercept, that's just a coordinate. I go over 0 and then up 7. So over 0, up 7, that's right there. And then I have two x-intercepts, one that's at -1, 0, so it starts at -1, 0 right there, and then another one that's at -7, 0, so I go to the left 7 and up 0, like that. All right, I even have the end behavior. It starts on the left-hand side, so to the left of our intercepts pointing downwards, and then the end behavior on the right-hand side points up, so at the very end, after all this stuff, it's going to end up pointing up like that. All right, so let's see how this is going to work out. So the end behavior starts here, and then we're going to go up to this intercept over here at -7. And at -7, it has a multiplicity of 1, so it's going to cross directly through the x-axis there. Then eventually it's going to make its way back down over to this next intercept at -1. And at -1, it has a multiplicity of 2, so that means that it's going to deflect off of the x-axis. So it's going to deflect right off of it. It's going to head right through that point over there at 0, 7, and it's just going to continue to point upwards from there as it keeps graphing. And then, you can kind of get a better idea of how the graph's going to look if you just graph it out. So if I graph it out on my calculator, let's see here. So x to the third plus 9x squared plus 15x plus 7. Okay, hit graph. And there's the same exact graph that I have. It doesn't look exactly the same because it looks like this part goes like way up above the graph and then back down. So even though I don't have that giant hump that goes through there, it's okay. I can just keep it like this because I don't want like a really super accurate polynomial. I want you to, use the stuff that you have here and graph them out. That's how you get the points for this. Okay, so that's 2.7. If you have any questions, please let me know. Email me or whatever you can. All right, that's it.